it's an honor to be here, and I appreciate CABBI for supporting me, supporting my research. I've really enjoyed working with CABBI through the last few years and interacting with people. I'm going to talk a little bit about heterogeneous catalysis. My field is a different type of catalysis. It's heterogeneous catalysis, and we've really been working for the last 23 years taking different heterogeneous catalysts and trying to take biomass-derived molecules and making fuels and chemicals from them using heterogeneous catalysis. Here's a collage of different industrial catalysts that are manufactured today. On the bottom left-hand corner, you can see that collage. Everybody who drives a car has one of these catalysts in their catalytic converter. You can see that there's the monolith there where you're placing a small amount of platinum and rhodium on there. It's worth several $100s that takes your processes in there. Most processes that make fuels and chemicals today rely on a heterogeneous catalyst, okay? It's been estimated that about 10% of our GDP comes through some type of catalytic process where you take some raw material, usually it's fossil fuels. It's going to, in the future, I believe it's going to be a biomass-based source, and you catalytically convert that. The big advantage of these are they are solid catalysts, okay? You can see them. Your catalyst in your catalytic converter, it stays there for several years, 5, 10 years before you need to replace it, because it'll be poisoned or there'll be attrition or some form of deactivation. Several important catalytic processes, probably one of the most important is ammonia synthesis. It's been argued that it's the most important innovation that's ever happened in humankind, has allowed our population. Without this ammonia synthesis process, we could probably only sustain a few billion people on the earth. And the reason why we can grow more biomass, feed more people, is because of ammonia. Great book to read about. It's really a book about catalysis, how I read it. It was The Alchemy of Air. If you want to read that book, excellent book. I recommend everybody in this field read it. So what is a catalyst? Well, a catalyst is a material that accelerates the rate of reaction, thereby increasing the selectivity of a desired product, and in the process is cyclically regenerated. Okay, so that's the definition of a catalyst. We can imagine there's some reaction we want to do. We'll start with a very simple reaction, A going to B. There's some transition state that this reaction has to go through, and what the catalyst does is it reacts with this transition state and lowers the activation energy for this transition state. And in reality, you have lots of different reactions. So we'll go to a more complicated reaction. A goes to B. B is your desired product. C is your undesired product. So you want to try and find a catalyst that will lower the activation energy to B. And in reality, you'll have hundreds of different activation energies, different elementary steps, and the whole reaction mechanism gets very complicated when you study catalysts. Now, these are also solid catalysts. Okay, so you take your catalyst, it's in some reactor. In this case, I'm going to show you a packed bed reactor. There's pores inside there. It's all about surface area. If you're making a catalyst with platinum, that platinum is very expensive, so you want to really maximize that surface area, get as much as possible. And there's these different steps you have to worry about. There's a film, that's a gas film or liquid film that's going to be flowing around this catalyst pellets. You have to think about diffusion through that film. You have to think about diffusion through the pores, absorption on the catalyst surface, and then there's some surface reaction. And that's where all the chemistry takes place. The rest is just transport. Then you have desorption, internal transport, external transport. So when you study catalysis, you also have to understand about transport and the transport in there. This is a scheme of the modern petroleum refinery. I think petroleum refineries are super interesting processes. It's a very complex system. You have all these different highly optimized unit operations. The modern refinery really has allowed us to extract more value from a barrel of oil. The first product you made from oil was kerosene, replace your kerosene lamp. Over time, we've learned how to extract more and more value from each drop of that barrel of oil. I think it's critical we learn how to do that from biomass as well, and we learn how to extract as much value from each part of the plant as possible. We've been able to process dirtier and dirtier oil feedstocks, make a wider variety of products, and in most of these blocks, most of the blocks where there's some type of chemical reaction involved, you're usually using this heterogeneous catalyst because it can stay in there. It hopefully doesn't deactivate fast, and then you can make a wide variety of products from it. And this is really a pretty new field. This is a bibliometric study we did in 2009, where we looked at how many papers were published that took catalyst and looked and studied biomass conversion with some type of catalyst. And you can see in 2000 there was 13, 14 papers that were published in this. It's grown dramatically now. Probably 20 to 30% of the papers in the catalysis field are something related with biomass. Okay, so what is the challenge? You know, the challenge is your biomass-derived molecules. They have a high functionality. They have oxygen on there. This is a slide I made actually for my PhD research in 2005, and I still use it to kind of explain the challenge. It's how do you take this highly functionalized oxygen molecule and remove some of the functionality, improve the thermal stability. You want to make a fuel. We heard about SAF. You want to take something like a vegetable oil, remove that oxygen, make it something that has the same properties as a sustainable aviation fuel, different types of chemicals. The challenge is, what is your carbon yield? A lot of these processes have low overall carbon yields. You want to increase the energy density of your feedstock. Your fuels, your liquid fuels, if you take a molecule like hexene or toluene, they have very high energy densities. So you want to remove as much of that oxygen as possible and make a fuel that fits into that infrastructure for diesel, sustainable aviation fuels, or some type of chemicals. Here's one of the catalysts that we use. This is a catalyst. There's over 6 million tons of this catalyst called a zeolite or a micro sieve. Okay, it's made from silicon alumina. On this diagram, there's silicon alumina. If I rotate it around, there's a three-dimensional structure. You can kind of see that in these diagram where you see those blue solid lines. That's the porous network. It's kind of a zigzag pattern. You can look at a couple different dimensions, but these pores are on the same size as a benzene or toluene molecule, so you can think about them as microporous material. There's really a big market for these zeolites. They're used all the time in petroleum refinery. It's $12.6 billion per year of zeolites, 6 million tons produced. 47% of the zeolites are used as catalysts in some type of usually oil refining reaction. So when we had this idea, can we take these zeolites and use them to convert biomass? And this is a paper we wrote in a long time ago, 2008. We took some biomass, we catalytically convert it, and we make aromatics. Aromatics are used to make chemicals, make fuels from them. We took a long time, but then we built this plant in Texas to take the biomass. We took loblolly pine. We have to remove the minerals because the minerals are actually poisons. They're nutrients for your biomass. They're poisons for your catalyst. So we have to remove them from the biomass, and we fed them in here, and then we were able to make the aromatics. And then we took that and we actually made a PET bottle. So this is a PET bottle that's made from wood. Okay, so it fits perfectly into the existing infrastructure. You're really capturing carbon from the air, and you're using it to material that can be infinitely recycled. There's a great recycling infrastructure for actually PET plastic. So a great way to capture carbon, use biomass to make that, and then catalytically can convert that. And really, all the same products you make from oil, in my laboratory, we can make from biomass and renewable resources. The challenge is cost. The challenge is economics, getting to the same scales that you get with petroleum refinery. So that's, in this project, we're making chemicals that have existing markets, existing infrastructures. We can also make a gasoline jet fuel blend as well with this technology. So we've also looked at trying to make higher value products. This is a graph of price versus volume. This is one chemical we've looked at trying to make. This is 1,6-hexane diol. You can see it's a higher value, over $4,000 a ton, smaller market size. You like this, it has what's called an alpha-omega functionality. There's hydroxyl groups on both ends of this 1,6-hexane diol molecule, and that's good to make polymers. Okay, the polymer people, they like that functionality. They can take that functionality and use that to make a range of different plastics, okay, from them. And so there's really large cost furfural that's available. If you look at furfural, there's over 600 kilotons of furfural produced per year. It's the largest biomass-based chemical that's produced worldwide. Most of the production is in Asia. Okay, you can see largest production is in Asia. There's a plant in Dominican Republic. There's also a plant in South Africa as well. And you can backward integrate to paper mills, other technologies to take furfural and make chemicals with it. So we developed a route to take furfural, and we made another alpha-omega diol called 1,5-pentane diol. Okay, and we use different catalytic approaches. We developed a 4-step catalytic approach to take furfural, make 1,5-pentane diol. It's really a replacement for 1,6-hexane diol. It's a very hard molecule to make from oil because there's not a lot of C5 feedstocks from oil. With biomass, with the hemicellulose sugars, you have a C5 feedstock. We can take advantage of that, and we can make this new functional molecule that can be used to make new types of polymers. The costs are dramatically lower, and we've actually been able to make ton quantities of this 1,5-pentane diol. We're looking at trying to build a commercial plant to take furfural and then convert it into 1,5-pentane diol. So heterogeneous catalysis really allow you to take advantage of the functionality of biomass. There's lots of functionality you get when the biomass grows. The oxygen is already there. The petroleum refinery, it's built on adding that oxygen back into these feedstocks that have a low functionality. We can make all the products you make from petroleum. It's challenging to compete economically because of the scale you are at with oil. We can also make new types of chemicals that are expensive to make from and almost impossible to make from petroleum. Okay, the key advantage here is they're solids, easy to separate from the products and reactants. We've really only started looking at this field in the last 20 years, and it's grown dramatically. And it's exciting to be here with CABBI to look at how we can use catalysis to make new products from biomass.